This lesson deals with complex algebra. You can find these notes in the course ebook in Chapter 4 starting on page 11. Let's take a look at first using addition with complex numbers. And let's look at polar form first. Suppose I have two vectors, call it x1 and x2, and I want to add those together, where x1 has a length of 10 and an angle of minus 45 degrees. And the vector x2 has a length of 5 and an angle of 30. Let's draw those out. Here's a length of 10 at an angle of minus 45. Here's a length of 5 with an angle of plus 30. You may recall from geometry, the way to add two vectors is to slide this one over to here, and then add those two together by finding their resultant. That would be this longer one right here. I did my best to measure this. This is about 12.3 using a ruler, and then I measured this angle in here, and that was a negative 21.8 degrees. As best as I could read it with a protractor. That's one way that you can add two complex numbers. Let's take a look at another way of doing that. Let's convert x1 to rectangular form. It had a length of 10 and an angle of minus 45. So the real part is 10 times the cosine of minus 45 plus j 10 times the sine of minus 45. This turns out to be 7.07, and this turns out to be a minus 7.07. x2 has 5 at angle 30, so the real part is 5 times the cosine of 30 plus j 5 times the sine of 30. This turns out to be 4.33, and this turns out to be 2.5. Adding these two together, take the first result plus the second result. We're going to add these two terms together because they're both real, and that gives me 11.4. I'm going to add these two imaginary terms together. One's positive and one's negative, and the sum is equal to a negative 4.57 times j. So what I have here is that the real part of the sum is the sum of the real parts. I'm going to use this in another video. Now to compare answers, let's convert this last answer to polar form. The magnitude is the square root of the sum of the squares of the real part squared, which is 11.4, and the imaginary term, not the j, but what multiplies the j, a minus 4.57. This turns out to be 12.28. Pretty close to what I measured with a ruler, but this is a little more accurate. The angle is the arctangent of the imaginary term over the real term, and that's equal to minus 21.84. For my protractor, I measured minus 21.8. Again, very close, but this is more accurate. The problem with this last one is that the arctangent of minus 4.57 over 11.4 is not the same as a plus 4.57 over a minus 11.4. This puts you in the fourth quadrant. If you put the minus sign over here, you'd have a real part that's negative and the imaginary part is positive. That would put you in the second quadrant. Be very careful when you take the arctangent. Now, one way to avoid this is to get a calculator that can actually do the conversion for you. You enter two things, in this case the real part and the imaginary part, and then you hit two buttons and you get the magnitude and angle out. These are called scientific calculators. Last thing to note here is that addition in rectangular form is more accurate than doing it in polar form. It's actually a lot faster. So why would we ever want to do it in polar form? Well, if we're doing symbolic manipulation of vectors, we don't have numbers to multiply out, so we would have to do it in polar form. But most of the time we're doing numerical problems, and this will be much quicker if we do it in rectangular form. Let's next take a look at multiplying two complex numbers. Again, let's start with polar form. Suppose I have x1 and x2. I'm going to multiply them together. And suppose this time x1 is 7 at angle 60, and x2 is 11 at minus 85 degrees. Let's convert these back to their definitions, which is 7 times e to the j60. This is a shorthand notation for this. This would be 11 times e to the minus j85. If we're going to multiply these two numbers, we multiply the magnitudes, we get 77. We just add the angles. And that turns out to be a minus j25 degrees. We can write this in a shorthand notation of the magnitude and the angle. Let's do the same problem in rectangular form. So let's convert our x1 from a magnitude of 7 and an angle of 60 into rectangular form. So 7 times the cosine of 60 plus j 7 times the sine of 60. That turned out to be 3.5 and j 6.062. For x2, we had 11 at minus 85. The cosine of that plus j 11 times the sine of minus 85 is 0.959 minus j 10.958. We're going to multiply these two together. Here's my value of x1 and my value of x2 in rectangular form. I multiplied this term times this one. That gave me 3.3565. Then I multiplied this term times this one. I get a minus j, and then the 3.5 times the 10.958 was 38.353. Then I multiplied these two and got a j 5.813. And then I multiplied this term times this one. Now I've got a j times a j, which is j squared, which is minus 1, times another minus 1, I get a plus. The 6.062 times the 10.958 was 66.427. Adding up the real part, I get 69.7835. Adding the two imaginary parts together, one of which is negative, I get a value of minus j 32.54. That compares with the last answer. I'm going to plug this in my calculator. Got to put two numbers in, get two numbers out. In this case, I get 77 at an angle of minus 25 degrees. I get exactly the same answer I had when we did it in polar form. The technique for doing this on your scientific calculator is usually explained in the little booklet that comes with it. I'm sure you can find it online, but it's not intuitive. Every calculator is a little bit different, and so you need to learn how to do this with your calculator. And one last observation, that multiplication in polar form was a lot easier and much quicker than doing rectangular form because of all this inner product type stuff. Why would we do one over the other? Usually when you have a symbolic problem, you have to do it this way. If we can pick either one, we'll pick the easier of the two. Let's now take a look at division of complex numbers. And again, let's start with polar form. Suppose I have an x1 that's equal to 6 at angle 120 and a value of x2 that's 3 at angle of 60. Let's take their ratio. x1 was 6 at angle 120. Write that as its definition of 6 times e to the j 120. x2 was 3 at angle 60, so write that as 3 times e to the j 60. The ratio of these two would be 6 divided by 3, and then we would take the argument of the numerator and subtract that of the denominator, so it'd be 120 minus 60 times j. We have 2 times e to the j 60. Our shorthand notation is 2 at angle 60. Punching this in my calculator, I convert from polar form to rectangular. I get 1 plus j 1.732. You can see how convenient that is versus taking our definitions of sines and cosines and the like. Let's do the same problem in rectangular form. Let's convert x1, which was 6 at angle 120. Punch that in my calculator, I get minus 3 plus j 5.196, and then x2 was 3 at angle 60, and that turned out to be 1.5 plus j 2.598. What I want to do is I want to make the denominator real. I want to multiply the denominator by what's called a complex conjugate, and that's the same number with j replaced by minus j. Now, to have no effect on this, I need to multiply the numerator by the same term. Let's multiply all this out. The minus 3 times the 1.5 is a minus 4.5. The minus 3 times the minus j 2.598 is a plus j 7.794. The j 5.196 times 1.5 is a j 7.794. And multiplying these two together, again, I get a j squared, which is minus 1, times another minus sign, which gives me a plus sign. And the 5.196 times the 2.598 is 13.5. Now for the denominator, I'm going to multiply 1.5 times 1.5, so I get the real part squared. Then 1.5 times this minus j 2.598 is a minus j 3.897. Then multiplying this term times this one, I get a plus j 3.897. Same two terms, but with an opposite sign. And then when I multiply this times this, again, I get a j squared, which is minus 1 times another minus 1, so I get a plus, and I get the imaginary term squared. So the inner product terms here cancel because they have the same term, but with an opposite sign of j. When you multiply by the complex conjugate, you just get the real part squared plus the imaginary part squared. That turns out to be equal to 9. Adding the real and the real, I get also a 9. Adding now these two imaginaries, I get actually twice 7.794. I get 9 divided by 9 is 1. The j 15.588 divided by 9 is j 1.732. Same result we had up on top. Clearly again, division in polar form was a lot quicker than doing it in rectangular form. If we can pick one or the other, we'll pick the easier of the two. But sometimes when we're doing symbolic work, we're forced to use this. This is the only way we can solve the problem. This is how you do complex algebra.